This movie will describe a collaboration by ABB, DLI Engineering, OMDEC, and Oceana Sensor Technologies to demonstrate smart condition monitoring. A smart CBM program provides a residual life estimate that is reliable enough to be useful, a clear decision that supports the maintenance objectives of the asset in its operating context, a way to monitor its own effectiveness, and an inherent continuous improvement process. This demonstration will illustrate how smart CBM objectives may be realized. A variable frequency motor drive causes the motor to vary its speed over the life cycle of the physical asset. An unbalanced rotor induces vibrations over the entire structure, especially to the failure mechanism, which is that T component held in place by friction and spring force. When the frictional resistance to failure falls below the applied load, failure will occur. We don't know exactly when the mechanism will fail, but we do know that age, in addition to the vibration amplitude, is a significant factor. That is, the older the item is, the more likely it is to fail. To initiate a new operational cycle, the operator inserts the T into the spring-loaded holding device and positions the golf ball. He powers the motor drive, he hits Start Life Cycle on the console, and the condition monitoring system acquires data. The life of an item subject to a failure mode proceeds. Each reading of the data is called an inspection. At each inspection, an intelligent agent program estimates the remaining useful life. Eventually, it advises to preventively replace or repair the item. As each life cycle elapses, the console updates the key performance indicators, or KPIs, that allow the maintenance manager to assess the effectiveness of each CBM program. From among the reported CBM KPIs, we consult the Failure Estimate Performance Indicator. It measures the CBM program's ability to estimate the remaining useful life. For this life cycle, the error in the remaining useful life estimate was 22%. A maintenance manager should understand his CBM program's predictive capabilities. The time to replacement estimate performance histogram is another way to evaluate a CBM program's predictability. How well are we predicting the time to failure or preventive repair? The errors in the time to failure estimates may be distributed normally. The mean and standard deviation of the distribution is another measure of how predictable a predictive maintenance program is. For the same reason, all CBM programs should monitor their own performance via the hit ratio, KPI. The hit ratio is the number of potential failures divided by the total number of failures. A well-designed CBM program should permit few functional failures, but at minimal cost and with minimal loss of equipment availability. Yet another indicator of how well CBM programs accomplish their purpose is found in the hazard graph. The system plots the hazard rate for potential failures and functional failures. The closeness between these two curves represents the CBM program's ability to preempt functional failure and its consequences. To review, we set up an unbalanced rotor and a realistically behaved failure mechanism. Both age and the levels of vibration influence the probability of failure. We connected the accelerometer to Oceana Sensor's Bluetooth wireless digital signal processor, known as the ICM 2020. It sent the signal to Oceana's single board PC, wherein the exact intelligent decision agent processed the data. The results were recorded by ABB's Asset Optimizer workplace. The vertical axis on the green, yellow, and red graph quantifies the factors that influence the risk of failure. This CBM decision model balances risk so as to minimize the long-run cost of operating the asset. DLI Engineering's Expert Alert agent uses advanced human knowledge to further refine the CBM decision process. The plant operator summary displays up-to-the-minute machinery condition assessment, including remaining life, fault diagnosis, and repair recommendation. The maintenance technician may interrogate Expert Alert and receive a focused display of vibration and process readings. Each feature on the vibration spectrum maps to a particular failure mode in the Expert Alert knowledge base. The technician may examine the diagnostic rationale that DLI's Expert Alert agent used to arrive at its diagnosis and recommendations. Expert Alert, via the connectivity of ABB's Asset Optimizer workplace, initiates a work order in the CMMS. Let's now examine the decision model more thoroughly. How did we develop the green, yellow, and red decision graph that ultimately led to the issuance of a proactive work order? We'll show you. The analyst empties all databases so that he can start with a clean slate. He uses Windows Notepad to edit a configuration file. By changing a key value to 1, the program will now run in experience acquisition mode. In this mode, we gather a sample of operational and maintenance data. We'll use that sample to build our decision model. We select the speed profile on the drive. We will build our sample using a variety of speed profiles covering the range of operating experience. Set up the failure mechanism. And start the motor. A failure has occurred. This constitutes one data point in our statistical sample. Let's continue to gather more data. However, next time, we will intervene preventively prior to failure. When operating, we use all inspection techniques at our disposal to avoid functional failures. We may monitor the situation, possibly using a form of time-based preventive maintenance. We notice at this time that a potential failure has in fact occurred. Based on a visual inspection, we ascertain that a functional failure is imminent. Hence, we stop the unit and perform preventive maintenance. How should we record this information in our CMMS in order that it can be analyzed and used in a predictive data interpretation model? The secret to a continuously improving CBM program is good recorded information. In maintenance, we must capture the 5 reliability-centered knowledge elements each time a work order is closed. Once the database has recorded a number of life cycles, it is time to use that data to build a predictive model using the exact program. There are 3 sets of procedures in the exact modeling program that allow us to construct, test, and export an optimal CBM decision model. We select those monitored variables that are likely to influence the probability of failure. Proportional hazard modeling has determined that the RMS vibration level is a significant variable. It has also determined that the shape parameter is significant. This means, regarding this failure mode, the working age of the component influences the asset's probability of failure. Hence, the decision model will incorporate both these factors. The final modeling step produces the decision model. The decision model blends in additional information, including economic factors. Once fully tested, we export the model to the decision agent program. The decision agent will assess incoming condition monitoring data on an ongoing basis. Thanks for viewing this movie. For more details or information, contact us.